Okay, so in this video, we're going to look at the area under a curve. Now, essentially, we are going to do this when we are looking at shapes that we can't easily find an area for. So we're not going to use this method for rectangles or triangles or a circle or half circle or something, but it's going to be for unfamiliar shapes. Now, this one is going to find the exact value of the area under a curve using a definite integral. For the approximate version, go look at the rectangles video, but this will give you the exact value. Now, a couple of things to note before we proceed into examples is that if a graph is above an x-axis, the integral that you get from evaluating it will be a positive result. If it goes below the axis at all, it'll give you a negative result. So if I draw a graph like this, if I evaluate the integral in this area, it'll come up with negative, which is an issue for area, but all you do is put another negative in front of it. That's what this is telling you to do here. So if it's below the axis, this thing here gives you a negative number, but another negative at the front undoes that negative and you get a positive result. The other option is to switch the terminals. Switching the terminals in a definite integral turns it from being a negative to a positive, or vice versa. So you need to remember one of those two methods. If it goes above and below the axis, like the one I just drew then, or a good one is a cubic or something, does this. You get a little section below and a little section above. You need to split it halfway through. I'm going to call that point C. That A and B, you're going to have this integral plus that integral. But this one here will give you a negative result. So, of course, you need to reverse the terminals like this one says, or put a negative at the front like this one says. You have to do one of those things to be able to find the area. So we've got 3 examples here from memory. Let's do them. Calculate the area under the graph of this function over the interval. It's always useful to have a general idea of what the graph looks like. You don't have to do it. It's not going to be worth marks unless they have asked you to, but it's always a good idea to draw it. Now we have a graph of 1/2 e to the 3x. We know that is an exponential graph. X equals 0 will give me e to the 0 being 1. Times it by a half will be a half, so that y-intercept is a half. It is a positive power, which means it must be coming from this side and then going up like that. So when I'm asked to find the area between these 2 points of -1 and 2, it's looking something like -1 there to 2 there. Something like that is the area we're trying to find. Now you can clearly see here the graph does not cross the x-axis and the graph is always positive, so we don't have to worry about the integral becoming negative anyway. So what we want to do now is simply find the definite integral. So it's going to be the integral between 1 and 3 of the function 1/2 e to the 3x dx. Make sure notation is correct, and there we integrate. So we know the antiderivative of e to the 3x is 1/3 e to the 3x. But don't forget we also have a 1/2 out the front multiplying. Now 1/2 times 1/3 we know gives you 1/6. That's between -1 and 3. Next step is to substitute these values in. Go check out the definite integrals video to help you do that if you've forgotten. So you put the 3 in, minus, put the -1 in. And just to tidy it up at the end, you can leave it as e to the 9 minus e to the -3. And because we're now using area, we'll call it units squared. It's okay, we don't know what the number is, but that is okay. We'll leave it as it is. My graph, by the way, is clearly not drawn to scale. Next one, find the area bound by the curve, the x-axis and the y-axis. So let's have a look what this graph looks like first. So it's a square root graph, so it must look like this because there's a positive in front of the root and a positive in front of the x. The end point happens when this thing here equals 0, and that's going to be -2. So it's going to start at -2 here. If I let x equal 0 for the y-intercept, that disappears. So you get square root of 4, which is 2. So we have, that's the graph, and it says bound by the curve. Yep. the x-axis, which is this one, and the y-axis, this one. So it's bound by those three lines, meaning in there. Again, you can see it doesn't go below the axis, so it's always going to be positive with the integral, so I can launch straight into integration now. The integral between -2 being the lower value to 0 being the upper value of 2x plus 4 as a square root, which I'm going to write as power of 1/2 because it's a bit easier to anti-differentiate that way. And then I'm going to anti-differentiate by using the rules we learnt last time. Check those rules out. So 2x plus 4, you raise the power of 1/2 by 1 and gives you 3/2, and you divide by that new power. Now, dividing by 3/2 is equivalent to multiplying by 2/3. But don't forget, we also need to divide by that 2 at the front, because if I differentiate, that comes out. So you have an extra 2 down the bottom, which then cancels with the 2 at the top. So what you really end up with is a 1/3 appearing here, because half of 2/3 is 1/3, and put -2 and 0 in here. Now I'm going to substitute 0 in, so 1/3, 2 times 0 plus 4 to the power of 3 on 2, minus 1/3, 2 times -2 plus 4 to the power of 3/2, like that. That gives you 1/3, 2 times 0 plus 4, you get 4 to the power of 3/2, minus 1/3, 2 times -2 is -4, plus 4 is 0, so 0 to the power of 3/2. And then you simplify that there. 4 to the power of 3/2 is the same thing as 8, and that gives you 8/3. And that's going to be in units squared. 0 to the power of 3/2, of course, being 0. If you forgot how to do 4 to the power of 3 on 2, remember that's the same as square root of 4. You'd have to write the 2 normally, and then cubed. Last one, calculate the area bound by the line y equals and the lines x equals 1, x equals 4. Well, first of all, what does this graph look like? Well, x minus 2 gives you a turning point of 2, and the -1 is here. The x-intercepts of this thing, if I factor this, or if I can isolate x, you get these equations here. You end up with 1 and 3. So there and there. So the graph does something like, whoops, that's not very to scale. Something like this. A 3 there, a 1 there. Now you've been asked to find the area between 4 and 1, which is that area there. So it's above and it's below. So now we need to account for that difference by splitting it across two different integrals. So the area is given by the integral between 1 and 3 of our function x minus 2 squared take 1 dx, plus the integral between 3 and 4 of x minus 2 squared take 1 dx. Now this first one here is going to give me a negative result. So remember, either we put a negative at the front, which works fine, or my preferred method is just to switch the signs around, the terminals around, sorry, make it 3 and 1, and that'll undo that negative. Now it's a matter of integrating. So anti-differentiating x minus 2 squared gives me x minus 2 cubed over 3. And -1 becomes -x. That's between 3 and 1. Plus, it's going to be the same thing here, the same integral, cubed over 3, minus x between 3 and 4. And then we substitute and solve. So 1 goes in there, so you get 1 minus 2 cubed over 3 minus 1. Take away, we now substitute 3 in, so 3 minus 2 cubed over 3, take away 3. Plus 4 goes in, 4 minus 2 cubed over 3, take away 4. Minus 3 goes in, so 3 take away 2 cubed over 3 minus 3 again, like that. So remembering, of course, this half corresponds to all this, and this half corresponds to all of this. And it's a matter of simplifying it all. So 1 minus 2 cubed is negative 1 over 3. Take 1. 3 minus 2 is 1. 1 cubed is 1 over 3 again, with a minus at the front is minus 1/3. Negative of negative 3 is positive 3. 4 minus 2 is 2, so 2 cubed is 8. Minus 4. Again, 1 cubed over 3, a minus, it's minus 1 cubed. 2 negatives make a positive 3, and we finish it off. So you have 3 plus 3 is 6. Take away 4 is 2. Take away 1 is 1. Then you have 8 over 3 minus 1, it's 7, minus another one 6, minus another one is 5. So plus 5 over 3, and together that'll give you 8 over 3. Once again, units squared. And that is how you find the area under a curve. And excuse the child coming in the background.